understand graphs, and they're still very successful today. And they really lead up to what we now understand as graph neural networks. And then give an introduction to graph neural networks and revise some of the applications. And then we'll have maybe some time for questions. And then I'll go through part 2 of my talk, which is about one particular application that I'd like to dive into a bit deeper and show one particular example model, which is around modeling dynamical physical systems using graph neural networks, basically learning to simulate the world using graph neural networks. And in this aspect, one can also ask questions around inferring interactions between particles, like kind of doing science, so to say, just from observational data. So start with part 1. And just to get everyone on the same page, let's maybe introduce what we mean by graphs and networks. So for our purposes, graphs or networks, so I really treat them as synonyms here. They're really just a connection of entities or nodes. So these are kind of the dots here in this figure on the right, and their pairwise interactions or relations. And these would be like the links or the edges between them. So I'll just use mostly the words nodes and edges from now on. And if we want to kind of define these and assign some symbols for those, then a graph, we usually use this capital G here, and it's a tuple of a set of nodes and a set of edges. And the nodes, I'm just going to use an index notation. So node is just indexed by its index I, and an edge is basically just a tuple of 2 indices that defines which 2 nodes are connected. On top of that, and that's especially important for machine learning, we're going to have features, and these are embeddings or features or any kind of high-dimensional vector description of both a node and an edge. So we can not only have that on nodes, where a node could be an image in a web graph, but we can also have that on the interactions between them, on the edges. And so we can also have edge features, H, I, J in this case. So these are kind of the core notations that are good to keep in mind, but they're going to be clear throughout the rest of the talk, I hope. And so the only other kind of core representation that is really important to think about when you look at a graph, or to know if you want to represent a graph just in a computer, is the adjacency matrix. And so let's say we have this really simple toy graph here with just 4 nodes and a handful of edges between them. Then we can represent this just in this very simple binary matrix, where we put a 1 wherever 2 nodes are connected, like the red one and the green one. And note that this is symmetric. So the green one is similarly connected to the red one as the red one is connected to the green one. So we put a 1 in both and zeros everywhere else. So it's kind of a sparse matrix. And now, of course, this is just the simplest form of a graph representation. And there are many typical variants. Like you can have directed graphs where edges go in a certain direction only, and then you don't have a symmetric matrix, but maybe only a 1 in like the upper diagonal part of the matrix. You can have weighted graphs where instead of a 1 and a 0, you put things like a continuous number in there, like a 0.5 that describes how much are 2 nodes related. But you can also have things like multi-relational graphs where you don't just have a single relation between 2 nodes, but let's say you have multiple adjacency matrices, one for each relation type. And then you can say, okay, adjacency matrix for relation type 1, these 2 are connected. Adjacency matrix for relation type 2, these 2 are connected under this relation, and so forth. And so this is going to be important for, say, chemical molecules where you have different bond types, or knowledge graphs where you have different relation types. And then a very typical trick we do is we also introduce self-connections, so that nodes can be connected to themselves, and then we just put 1s on the diagonal. This just means adjacency matrix plus the identity matrix. All right, so the typical supervised tasks on graphs that we care about in machine learning, and this is really like where are we going to use those models downstream? Like we can learn representations unsupervised, but ultimately we kind of want to use them for something. And the typical supervised tasks that are most relevant in the literature are node classification, or any kind of prediction task on a node. And this, for example, in this graph here, we might want to classify what this node here means. It's an apple in this case, just based on its relations. Things like link prediction is another very important task that operates not on the nodes, but on the edges, on the links between two nodes. And for example, we have this little social network here where we know certain people are friends with each other. But then the question is, are these two people also friends? Just given the social network and maybe their node features that we have about them. And lastly, we have graph level prediction tasks or graph classification as one particular example. And this is, for example, if you have a molecule and you want to ask the question, is this molecule toxic or is it safe? And this is something a machine learning model can learn just based on the statistical properties of a data set where you maybe have a few labels around toxic or non-toxic molecules. A machine learning model, a graph neural network in particular, can look at a new molecule and tell you if it's toxic or not. And so graph representation learning, which kind of precedes graph neural networks, is really about the problem of learning, say, an embedding of or a representation of a graph. And so let's say you have a graph like here, and you learn this function that takes this graph as an input and then gives you an embedding for every node on the graph. An embedding really is just like a learned vector representation of each graph that you can, like, say, plot in this embedding space. And this can be high dimensional. Here I'm just showing a two-dimensional embedding. Now, before we go to graph neural networks, I just want to revise some of the some important concepts around embedding learning methods, because it's really important to understand where we're coming from when we look at like graphs and learning representations about graphs before we go into like the benefits of why do we even need a graph neural network. Because a lot of problems on graphs, and if you're a practitioner, you don't need graph neural networks. You can really just use simple graph learning or graph embedding methods. And so the goal here is really to learn structural node representations. And that's the important bit here. You really want to learn representations of nodes that are informed by the structure of the graph. If you just want to learn representations of nodes and ignore the graph, then this is not graph representation learning, it's just representation learning. So the important bit here is that you use the structure of the graph to inform the representation you learn about the nodes in your graph. And this here, for example, a very typical setup for doing this is you have a graph and you learn an encoder for every node. Let's say if a feature for this node, you put it through a simple encoder that just looks at this particular node, gives you a representation, and then you train this representation using a pairwise scoring function. Let's say in this representation space, you know these two nodes are connected, the two green ones here, because you know they're connected in the graph. So you kind of want to score them in such a way that they're, for example, close to each other in representation space using a loss. And then you can train this with a optimization procedure, for example, gradient descent. And let's say we have these nodes I and j, then we call their representation zi and zj. And just to give a few examples of what this looks like in practice, and these are really simple techniques in practice, we, for example, want to embed nodes only based on their node ID. We don't have any other information. That's the simplest case. We just have a graph. We don't have any bridge feature information for the nodes. Let's say we only have an ID. So the ID describes just the index of a node in a graph, and this can be a randomly assigned index. Then some simple techniques you can view under this scoring function interpretation here. So for example, there's this technique called Laplacian eigenmaps, which effectively you can understand as it optimizes the following score function, which is basically the squared Euclidean distance between two nodes, zi and zj. And it wants this distance to be small or close to 0 when two nodes are connected in the graph, and large otherwise, or no particular kind of loss otherwise. And so what we do is we take the score function, multiply it with the adjacency matrix element for that particular edge, and then this is the loss, and we just sum this over all relations. So this adjacency matrix element here is going to be 0 for all the nodes that are not connected, so all of these don't receive a loss. And whenever this is 1, then the loss is basically just the squared Euclidean distance. And so what this does is it just pulls node representations together if they're connected in the graph. And another similar a similar setup is instead of taking the squared Euclidean distance, you can also try to optimize their alignment in latent space, like optimize their inner product. And so, for example, you might want to have their inner product be close to 1, which is what you get in this representation learning loss here. So here you would have the inner product, and you want this to be close to the adjacency matrix, so that the inner product basically, the matrix of inner product basically has the meaning of an adjacency matrix. And so what this does is effectively it puts node vectors that are connected, basically pairs of nodes that are connected in the graph, they're going to be similar. And representation vectors that are not connected in the graph are going to be dissimilar. They're going to be orthogonal, ideally, and have an inner product of 0. And then there is maybe one of the more popular techniques these days, which is called deep walk or node to vec. They both use the same mechanism. And what they do is they, instead of looking at like just pairs of nodes, they sample random walks on the graph. So basically paths on the graph. And then they score whether 2 nodes are close by on this random walk or far away. And basically, any node that is close by, for example, a direct neighbor, gets scored as positive. And this is a softmax function here, if you recognize that from maybe some earlier lectures. And everything that is far away from each other in this random walk is scored negatively or pushed away. And we train this using a cross entropy loss. So basically, we take the log of the softmax and then mask it with the adjacency matrix. And so this effectively gives you just already an overview of like what are typical ways of like learning embedding functions if you have a graph. But we don't really talk about like the encoders here yet. These are really just directly an immediate embedding of the node ID. So we directly backpropagate, for example, on these representation vectors. Now, if you want to train a method like this on a large graph, you will have to basically compute this loss here over all possible elements of the adjacency matrix, because you sum over indices I and j. And this is also going to be very important for graph neural networks, because effectively graphs can be very, very large, and the adjacency matrix grows quadratically in the number of nodes. And so computing all these possible node pairs in this loss function becomes prohibitively expensive. Let's say if you have 1 million nodes and you already have 1 million squared elements that you need to compute. And so the solution here is to sample, it's called negative sampling, or in this case, to sample negative edges. So instead of computing this loss for all elements of the adjacency matrix, you pick a pair that you want to compute the loss for, and you pick a random negative example, a random node that is not connected or somewhere far away in the graph. And then you have a loss that pulls the positive elements together and pushes a negative element far away. And this all of a sudden scales linearly in the number of edges. And so this is basically how all kind of practical link prediction methods are trained. Because all graph representation learning methods are trained, because you cannot afford to look at the full adjacency matrix. And so the negative example here would be this edge here, that these 2 nodes are not connected. And now in node to vec, we train effectively this loss that I showed you earlier. We approximate this using a binary cross entropy. We just say, okay, these 2 nodes are connected, so we're going to maximize the score, and we're going to minimize the score, that's a right-hand term, if they're not connected. And we sample 1 positive and 1 negative pair in every element of this loss here. And this is a very typical setup. So this is something you can scale, and this works remarkably well for graph representation learning, a simple method like this. And effectively, this is really just a binary cross-entropy classification loss. So you basically turn your representation learning task into a classification task. You pick pairs of nodes and say, are these connected? Yes. Then you assign a positive label. Or are these connected? No. You assign a negative label. And you do this for all the positive and negative sampled edges in your graph. So this is your set over which you compute the sum. And so this already, like this simple framework already gives you access to basically a very powerful representation learning for a lot of graphs. Now, what we haven't talked about so far is multi-relational graphs, things like knowledge graphs or chemical molecules, where you have not just a single edge type connected or not connected, but you have multiple discrete edge types. And for example, you have an edge type for grows on, an edge type for needs in this particular example, or different chemical bonds between atoms in a molecule. And so the only change we have to make to our graph description is, instead of just having a set of nodes and a set of edges, we also have a set of relation types, R. And then an edge is basically described by this triple here, an index, a relation type, and an index of the target node. And with this, you can basically already describe all kinds of knowledge bases. And if you now look into how like link prediction methods and knowledge graphs, for example, work, then these have they're very much specialized to this relational graph setup. And the only difference you really have to make is you have to put some embedding for the relation into the score function. So now, instead of having an inner product between Zi and Zj, you have a bilinear product between Zi, Zj, and this matrix for the relation R here that you also learn. And this is already kind of a state-of-the-art relational learning method for relational graphs. But you can also do something like, from this paper, transio, translational embeddings, where instead of an inner product, you say, okay, you want the representation of node I and node J to be similar after the representation of node I has been translated by a vector describing the relation. So basically, you say, okay, here is node embedding of node I, here's embedding of node J, and they're related with relation R. And the relation R basically tells you how much, what the difference is between these two vectors in this embedding space. And this is a very powerful method to learn embeddings and knowledge graphs. And as you later see, all of these score functions here can also become loss functions for graph neural networks once we get there. And again, you can train this with negative sampling and some binary cross entropy loss, or for transy, we use a margin loss typically, but the details here I'm not going to go into today. And as I mentioned before, this still forms the basis for many state-of-the-art knowledge graph completion methods. So maybe as a main takeaway, while graph neural networks are really, really exciting and powerful, you don't always need them immediately. And there are many benefits for sticking with simpler methods as well. But now let's talk about the limitations of these embedding learning methods and why ultimately we need graph neural networks to really solve a wide variety of tasks on graphs. And so these simple embedding learning methods, they can only embed node IDs, the ones I described earlier. They really start by embedding node IDs into a single vector. They just take the node ID and say, okay, this is vector for node ID for node ID 1, and then they directly optimize this vector. But this cannot generalize to new nodes at test time, because at test time you might get a new node with a new node index, but you don't have a vector for it because you haven't learned it. And there's also no parameter sharing between nodes. Like, for example, if two nodes are similar based on their features, they're both similar users in a social network, but maybe they have different social networks, then the model doesn't know about this. It doesn't share any parameters or any inductive bias between these. So every node is really independently embedded using a separately learned vector. And this is where the kind of solutions come in. So for example, you can make this embedding vector dependent on node features. So you could use an MLP or small neural net to compute this node embedding vector from some features that you have, like the features that describe a user in a social network. And then on top of that, you can also use message passing. And this is where graph neural networks come in to propagate features from neighboring nodes. So let's say you have two nodes in your graph and you have a new node coming in, like a new user signing up for a social network and connects with two friends. Then you can propagate those features from the neighboring nodes to that user and have a function that learns how these features should be propagated and adapted. And this is effectively where graph neural networks come in. And now let's talk about graph neural networks. So graph neural networks have been around for some time, at least in a kind of in some early forms. And there was, for example, this graph neural network model paper from Scarselli and others in 2009. The main limitations from graph neural networks back then, they were not really practical. They weren't really trained with gradient descent and modern like deep learning methods. And they haven't really found much attention back then. But effectively, the bigger picture is quite similar to how we use them today. And so the bigger picture is effectively you have a graph, and this graph is like your input to the model. And then you have multiple rounds of hidden layers or message passing layers, where every node, here, for example, this node in violet, is updated based on the neighboring nodes in this graph. And you do this for every node. You have some kind of activation or some update function in between. And then you do this again for the next layer in the model. And you keep on doing this, and effectively every layer passes messages along the edges of a graph. It agglomerates them or puts them all together and transforms them. And in this way, you can learn very, very diverse and powerful functions on a graph. Now, if you've already heard about convolutional neural nets on graphs, or convolutional neural nets on grids, such as images, then you can also view them under this message passing framework. Before I go there, I see there's one message on the chat. Let me quickly see that. Right, so the question is, so the hidden layers in this figure that I just showed earlier, are those also neural nets? And that's a really great question. So basically these hidden layers are effectively, so they can be neural networks. They can also be just a linear layer that transforms and then just has a linear update function. So ideally, to have the most powerful models, we want those hidden layers to be neural networks by themselves. But in a very simplest case, they can just be linear layers followed by a ReLU activation function. So we can go all the way from very simple, and it still works really well, like basically linear propagation, all the way to kind of full-blown per layer function approximators with deep neural nets itself. It's a really great question. Now, if we look at convolutional neural networks, then this already gives us the basis for how we can actually design graph neural networks in practice. And this was also for me, when I looked at graph convolutional networks back in the days, one of the starting points. And so we know convolutional networks these days are still kind of one of the core architectures for processing images next to transformers. And a single convolutional neural network layer usually does the following. You kind of swipe it over an image, and for every location, you have, like, say, for example, a 3x3 filter that transforms the local neighborhood and then gives you an update for the center pixel in the next layer. And so this is also represented here on the right-hand side, where you have these 9 nodes, which now describe one of these local neighborhoods, and the center pixel, which is updated. And I'm already drawing the arrows here, which is basically how the information flows. So you kind of can view this as a graph with a message passing operation. And now we just introduce a notation for each of these like nodes here, which are basically the activations of a pixel or of a pixel in the image or in a hidden layer. So we can enumerate them from H0 to H8 for all the 9 nodes. And then we can compute these updates for every single pixel in this graph representation. And this is basically just rewriting what a convolutional layer does. And so, for example, for this single pixel here, we have these messages, which are basically these arrows here on the edges, and they're simple messages in the form of a linear learnable parameter matrix multiplied. So a parameter matrix multiplied linearly with a hidden vector, and this is this activation for a pixel or node. And then in the center pixel, to get the representation for the next layer, we just add everything up. We add all these individual messages up. And so if you want to calculate the update for this node in the middle here, then the full update is basically for each of these arrows, we compute one of these linear updates. And these are different weight matrices for every type of neighbor. And then we pass it for an activation function, which for ConvNets is typically a ReLU, for example, a rectified linear unit. So just one of the simplest nonlinear activation functions. And so now we've kind of viewed like a convolutional neural network as message passing on a graph. And then going from there to like an overall message passing framework is a relatively small step. And that's what we're going to do next. I see there are more questions. Yeah, there's a question if I could give a practical example and explain the details of a graph neural network. That's a great question, and that's what's going to come in the next slide. So we're going to start now with a very simple undirected graph that we have here on the left. And in this simple undirected graph here, we now don't really have, like in the last slide, we had an upper left neighbor of a pixel, an upper right neighbor of a pixel, but now we have like just any kind of undirected graph in a social network, for example. And the method I'm going to explain is a class of convolution-based graph neural networks that also form the basis of graph convolutional networks. And so what we want to do here is for every layer in this graph neural network model, we want to calculate an update for every node in the graph. And let's say we want to do this now for this node in red. And so this node in red here gets messages from all the neighbors from each of those directions. And it has also a self-connection here in blue. And so basically information flows from the neighbors and also from itself to the next layer. And so this is kind of the simplest way of saying we want message passing from the neighbors. We just say, okay, information flows just in the local neighborhood, and every neighbor here is treated in the same way. And now this is the core kind of update function that we compute in one of those neural networks in every layer. And so here, I'm just coloring what these update functions look like for the blue arrow and the red arrows. And a full graph convolutional network would just be repeating this update function here a number of times. So like in the figure you saw earlier, this is kind of what's happening in a single layer of this model. And so in a single layer, we effectively have, first of all, like in a convolutional network, one linear message that gets passed to itself here in blue, just a matrix that we learn, and the node representation of the last layer. And then we have all these messages from the neighbors. And so this is where it gets interesting, because now we don't have information of how these neighbors are different anymore. Like in a social network, you don't have an upper right neighbor and upper left neighbor like in an image, but they are just your friends, for example, in a social network. And so the most straightforward thing you can do is you treat them all the same. So you assign the same learnable matrix here, like W1 in this case, for each of those neighbors, and you sum over all of them. And on top of that, we have an optional normalization constant that I'll talk about in a moment, and we sum over all the neighbor indices. So these are all the neighboring nodes for the center node here. Let me briefly look at the chat. I think there's some questions. And the question is, how do you choose the node? And so this is a great question. So basically, we do this for every node in the graph, and we do this in parallel. So we don't really iterate over every node in the graph. So what I'm showing here is just an example for what happens at one particular node. But in practice, this update here gets done simultaneously over the entire graph. So this is really what happens kind of all at the same time. And this is basically then just what happens on a single node in a single layer. And the question, and then there's also one question for nodes that are not so central, the information flow would be less as compared to more central nodes. And it's also a great question because some nodes, for example, this node in the top right here, would only be connected to one other node. And it kind of, to really learn about the node that's on the far left-hand side, it would have to do multiple message passing steps to get this information. And this is already hinting at one of the kind of frequently occurring issues in graph neural networks, which is that there's kind of a bottleneck. So for information to flow from this left-hand side node here to the right-hand side node, all the information has to flow over multiple message passing steps. And this is typically not a huge problem because you can just repeat this message passing operation multiple layers, and eventually that information is going to reach the node. And most real world graphs have like a small diameter, like you only need like 6 or 7 of those steps, and then information usually propagates. And there's one more question: are we considering a directed graph here? And the answer here is no. So what I'm showing here is really an undirected graph. I'm just showing that for an update for one particular node, the information flows in. But then if you consider the same update, what would happen for the top left node here, the information would flow the other way. It would flow to that direction. And so we don't specify the direction here. Everything always flows into the node. And therefore, we don't prescribe any direction on the graph. So it's an undirected graph. In a directed graph, you would only allow information to flow in the direction of the edge. So for example, if this edge here on the red node to the top left points the other way, then this red arrow here would disappear. No information would flow in this message passing step. All right, in the interest of time, let me go to a few remarks around this setup here. So I haven't talked about this optional normalization constant here. And this is important because now in convolutional neural networks, for example, on grids, on images, you always have one upper right neighbor, one upper left neighbor. There's always just one neighbor of every type. And you don't have to worry about all of a sudden having like 1,000 neighbors for one particular node. And so this is where it becomes, where the second challenge for graph neural network comes up, which is, so the first one I mentioned was like this problem of like information propagating along long paths. And the second problem that often arises that we have to deal with is that nodes can have very different numbers of neighbors. So one node can have one neighbor, but another node can have 1,000 neighbors. Or if you look at like social networks or something like Twitter, there can be nodes of 1 million followers that have 1 million neighbors or even more. And in this case, we need to figure out a way of how to deal with like this vastly different numbers of neighbors. And the simplest way is to normalize these messages, to just say, hey, instead of summing all of these messages up, we average them, for example. And averaging means we have a normalization constant here that is just 1 over the number of neighbors. Later, you'll see we can also learn this normalization constant and just pick out important neighbors and weigh them by their importance, for example. And so there's a lot of like design decisions in graph neural networks going into this normalization constant to make sure you get information from the right neighbors and you don't get overblown by all the information that comes in. And another just purely practical aspect, if you would not normalize just sum, then this sum could grow unbounded. This value could become very huge. And then if you do optimization with gradient descent later to find these parameters in a deep neural net, this could be very difficult to do. And so these are just some details here that are interesting to know. But like typically when you use some of these practical implementations that I'm going to point to later of graph neural networks, they all already take care of these normalization constants. And in graph convolutional networks, we made a particular choice here that I'm not going to go into details here. But basically, it ensures that information is always kind of bounded and doesn't blow up. And so instead of a sum, you can also choose other aggregation functions like a maximum. You don't even have to sum or average. You can also just do a maximum pooling. You just choose the maximum activation for each row in your vector here. This can also be a popular or powerful activation function. And now this, I haven't talked about the sigma here yet, but that's also an important aspect of a graph neural network. In the simplest case, what I showed in this figure earlier, you had every layer, and then in this layer, this is what the message passing looks like. And then you have this, what happens after the layer. And this can be a simple activation function, like a rectified linear unit, a ReLU, like in a CNN. But this can even be, as points to one of the questions that was asked earlier, can even be a neural net itself. So this can even be a deep neural net itself of like an MLP with 4 hidden layers or something like that. And that can make it more powerful. So you really have some choices here. The really important bit is that you do this message passing. And another aspect, what I haven't talked about yet, is if you go to really large graphs, like let's say you have graphs where nodes can have 1 million neighbors, then you typically don't want to compute this function here for all the 1 million neighbors because it gets really expensive. And one neat trick you can do is you can subsample those neighborhoods before you even feed it to the model. Like you can say, okay, we only sample 10 neighbors per node, and that's it. That's all we take into account. And we just hope that those 10 neighbors are the most important ones. Maybe you can a priori define what are the most important neighbors and so forth. So there are a lot of design decisions going into that. And that's also one of the questions that came up, like subsample the neighborhood on what basis? So in the simplest case, and this is what GraphSage is doing, really just randomly subsample. And it's surprisingly good to just randomly subsample. Because typically, if you take a random sample of a big pool of neighbors, typically this is still somewhat representative of what the neighborhood looks like. But this is not always the case. And there's a lot of papers and development in the field going into how you can do more informative subsampling, like according to some heuristics, like you subsample neighbors that have a high centrality or some kind of other aspect in the graph. Or that themselves have a lot of neighbors, for example. So you can define heuristics. You can even learn an importance function, but we're not going to go there in these details. But that's a really great question. And there was also a question: do we subsample neighborhoods based on Euclidean distance? So that's, again, that could be one of those heuristics. Like you could use a heuristic like that, like Euclidean distance, to subsample. But in principle, like there's many design decisions one can make here. And it's really up to the researcher or the practitioner to make these decisions. And this is even still an active area of research. So this is where like one can still potentially improve certain systems in certain aspects by coming up with better techniques for subsampling. Now this was what I just showed was one of the most basic and simple graph neural network variants. And when we published this, like the graph convolutional network, this was kind of the first really use case of this method for classifying nodes in the network. And we showed that this really, even this very simple method here, where we really, like when we published it, we didn't even do any subsampling, and we just had a very simple activation function here. But the simplicity is also what makes it quite powerful, because you can implement this in a few lines of code. And on small graphs, it runs really fast. Like as a PhD student, some of those experiments I could run on my laptop in like a matter of minutes. Only when going to bigger graph, I had to go to GPUs. And so this was really one of the reasons why this got picked up so massively, because it's so simple. And on the other hand, it still performs as a very strong baseline for many tasks. So it's still being used today in practice, even though this rule seems very simple. But of course, there's many improvements that have been developed by then, and I'm going to go into some of those now. So some of the more expressive graph neural network variants that we see today, they add, for example, relation types. So I already mentioned how we can do this for graph representation learning in the beginning, but we can do the same thing for graph neural networks. So we can also take into account not just a single relation in an undirected graph, but we can say, hey, we have different weight matrices that we learn for every relation type in the graph. And we have, for example, also different neighborhoods, like you see here on the right-hand side. For relation 1, we have maybe these neighbors. For relation n, we have these neighbors. And now I'm also showing directed graphs here. So the arrows could also point in various directions. And information is only allowed to flow in the direction of the arrow, for example. It's one heuristic one can apply. And then a very simple change to the update rule that works surprisingly well is just to assign different weight matrices for each relation and just sum over those relations. We can also assign a different normalization constant for each relation. And again, I'm not going to go into the detailed design choices here. So this is really up to the models. You can look up these models. For example, RGCN is one paper we published that makes certain more detailed design choices here. But you can find in typical deep learning libraries that implement many of these models, they make those design decisions for you. And then you get a certain performance. But of course, the interesting aspect is to play with these design decisions. Like instead of a sum here, you could also put a maximum here, or you could even put a concatenation operation here, because you only always have the same number of relation types in your graph. And if for example, in a molecule, you only have like, say, 3 or 4 relation types, then you can you can afford to concatenate them instead of summing them, which can, in certain cases, give you more expressivity. And now, so now that we've talked very briefly about adding support for relation types, the next step to get towards attention mechanisms is a very, very small step. And you've probably all heard about transformers today, which are like underpinning a lot of the recent advances in large-scale machine learning, both for language models and for vision models. Transformers can actually be viewed as effectively this update rule up here, but then with a not fixed normalization constant, but with a learnable normalization constant. What that means is that this alpha here just tells you how important is one neighboring node for the update. How important is neighbor X, neighbor 1, neighbor 2, and so forth, based on their features. And this is a simple yet very, very effective technique of learning kind of importance of neighbors. And if you do this, for example, on a text sequence, you can learn importance of say, word pairs, and then information gets routed that way. And that effectively gives you the basis of the transformer architecture. And so in transformers, those relation types here would be called heads or attention heads. So they can be viewed as in the same way as relation types in graphs. And the way typically that this attention coefficient or normalization coefficient here is computed is we take a softmax of a bilinear product. And so this exp divided by the sum of exp, that is really just a softmax activation function that you've probably seen already. And the argument here is the source node, the target node, and a learnable matrix between. Now in transformers, you usually have two learnable matrices in between, the query and the key matrix. And then this matrix up here is called the value matrix. I'm not going to go into those details here, but in a very kind of high level description, this is kind of what's roughly happening. So we effectively have an activation dependent normalization constant here. And there's, of course, many variants of this mechanism. So one variant is graph attention networks that takes the transformer update rule and changes this particular update rule here a little bit. And graph form is a recent paper that also takes a very similar mechanism and also puts it back closer to transformers. The main difference to transformers is here that we operate on a graph, and we pass messages only on the nodes that are connected in the graph. And so we don't attend to messages or don't attend to neighbors that are not connected in the graph. Whereas, for example, in language, you would attend to everything because usually you only have short sequences and you don't have this additional information of what is connected to each other. And so again, this bilinear product here basically tells you how are node I and node J related under this relation type, which is very similar to what we've seen for these graph embedding learning methods. But now we kind of put this little score function here in every layer of our model. We always compute a score function, how are those two nodes related on the fly, and use it to weigh the importance of those neighbors. And that effectively gives us a very powerful update rule for graph neural networks. Now, one last variant of graph neural networks, and I'm going to summarize them in the next slide, but one last variant I want to go into, which is very important for many applications, is the neural message passing formulation of graph neural networks. And this was first introduced in message passing neural networks, and then later refined in graph nets. It's what often DeepMind calls their graph neural network models. They call them often graph nets. And this is because there was one paper by Battaglia and others that introduced this formulation. And that formulation, effectively, what it says is instead of this way of looking at graph updates like before, you have like a linear method here that takes information from the neighbors, and then you have an activation function. This message passing formalism says, okay, for every edge, we have just a powerful edge function. So for every pair of nodes, we just have a powerful function. That function itself can be a neural network or complicated neural network. And then for every node, we also have a neural network that is applied. And so let's maybe quickly look into the details of this. So the edge update in this model takes into account both neighboring node features, both neighboring node embeddings. So HI and HJ, as I mentioned earlier, these are like the learned or hidden features of your network from each layer that describe the node I and node J here. And node I and node J are really like two connected nodes in this graph. And then you maybe even have some additional side information, edge features X, I, J. So this could be side information that your data provides you. So this is something that the model can also take into account in every layer. And F edge here is really just a small neural network, like an MLP, that operates on the concatenation of those feature vectors. So you just take all of these feature vectors, you put them in a big vector, and you apply an MLP. And now this gives you a very powerful representation of what this edge looks like. So you really learn a message or an edge update, like a hidden representation for an edge that really describes what this edge, the meaning of this edge in the graph, basically. And this, for example, if you apply this to a physical system, this could be the force or description of the force between two particles. And this is very often where this model is used for like describing physical systems. So then this edge function becomes like a force function that estimates an embedding of the forces between two particles based on all the information you have. And then the node update function basically takes all these messages, Hij, that we now computed, and aggregates all of them, for example, using a sum or some other aggregation operation. So we sum over all these neighboring messages, which is depicted here in this figure. So we have H21, H31, H41, all of these messages that come into this one node here that we just computed. We aggregate them all together. And then together with the node representation itself, and maybe some additional extra node features you might have, we compute now this update for this node here. And so effectively what we do here is we have a powerful edge function using, for example, MLP, and a powerful node function, and we iterate those. So if you want to build a deep neural network out of this, you would alternate between edge update, node update, edge update, node update, and so forth, just applying these two functions iteratively. And this gives you a very powerful representation that you can now, or a powerful model that you can use to really learn like complex physical dynamics or complex traffic simulation and so forth. So this is usually too expensive to run on large social networks, but it's something that if you really need a very complex function that you want to approximate, like a physical simulation, then this is like the way to go usually. Now let's do a quick summary of these main message passing variants or flavors. So the simplest one we looked in the beginning was this convolutional model, where you basically just have your neighboring nodes, and you have a linear function that you apply, like a linear transformation for all the neighbors and a linear transformation for the node itself, and you pass it through a node activation function, a node neural network. Then you have attentional models where on top of that, you learn this normalization or like importance factor for each pair of nodes, based on the neighboring features. And the most typical form is like this bilinear product. But then the most powerful version of these models is this message passing neural network, MPNN or GraphNets formulation, where you have edge updates and node updates, or even a global update that I'm omitting here, but you can also assign a global node if your graph is small that describes the graph at a global level, and also pass messages between that and the local nodes. And so this is kind of the overall framework of, if you want to think about graph neural networks, they typically always fall in these three categories. And it goes from simple to more expressive and also more expensive to run. So if you want to run something on a really large graph, then usually you want to start with the first one. If you have a medium-sized graph, but you want to learn something more expressive, you can then start typically to afford the second one. Whereas if you want to run like a complex physical simulation, for example, then you typically want to use the last one. Just one quick note on when you implement graph neural networks in practice. then typically what you see instead of those representations here, where you have a single node and describe how this node is updated based on its neighbors, you often see a matrix representation where the entire graph is described at the same time. And then this matrix representation here is really just stacking the individual node hidden vectors as row vectors into a matrix. So capital H here really describes the entire graph. Like capital H here describes the entire features of the entire graph in a single matrix. And then you have these updates here in a matrix form. And now these normalization constants here and the sum is now replaced with an adjacency matrix multiplication. So this basically now shows you how all of this is run in parallel. So you don't actually iterate over these indices I here bit by bit and run this in sequence, but you can run this entire update for the entire graph in parallel by just implementing this matrix multiplication here. And so this is how it's done in practice typically. And so there's one question here. Can we treat target and independent features and its weights as graph? And so I'm not sure if I understand the question, but let me maybe phrase it that way. So the let's say we have our input features and we have some relations between them. Then the input features would be this H here in the very first layer. This is how we would assemble our input features. And A would be the adjacency matrix that describes their relations. And then once we applied this rule here once, we get an update. And then later in the next layer, we take that updated H bar as input here and run the same thing again, maybe with different weight matrices. So we can iterate this update multiple times. And the targets that we want to predict, they don't come into this update. They come into the loss function that I'm going to talk about in a moment. All right. So now once we have this entire setup, we can look at this graph neural network setup here. And from this, we can now look into revisit those various tasks I talked about in the beginning, things like classification or link prediction, like the typical graph tasks. So now every single layer in this model here, and in the simplest case, if we use a graph convolutional network, is really just in every single layer, all we do is we do this matrix multiplication. Here's some adjacency matrix. I'm omitting now the separate term that I had in the last slide, this one here. And just putting it into a single representation here. And then every single iteration, what we do is we have the adjacency matrix and we multiply it with the hidden layer matrix of the activations. And in the first layer, these are just the input node features. And we have a learnable matrix of parameters here. And then we have an activation function. And so we just iterate that multiple times where we have different weights per layer. And after a number of these hidden layers, a number of steps, we get an output. And this output is effectively a matrix, capital Z here. And this matrix is just a vector of a matrix of node embedding vectors. So every row in this matrix here describes one node and the embedding we've now learned. So the model effectively produces embeddings for every single node in this graph. And so now we have various different downstream tasks we can apply here just based on this final node representation that we get out of the model. And in the simplest case for node classification, we can, for example, put a softmax classifier on top of every single node Zi here or Zn. We can do the same thing for graph classification, where we first aggregate all the nodes in a graph in a single global representation by, for example, taking a sum or an average over all the nodes in your graph. Then you have a global descriptor of the graph, and we can put those in a softmax classifier, either by directly applying a softmax or before that having like a small neural network there that we use to make the summary of the graph a bit more predictive for the graph classification task. And lastly, we can also look into link prediction by taking these node representations that we calculated here and take pairs of them and just score them with an inner product to predict the adjacency matrix elements. And again, this is really something that we've already seen in the graph representation learning introduction I gave you earlier on, if we have these inner products here, they predict how aligned two nodes are. And we can use the same loss function and the same scoring here for link prediction of these models. And we can use those negative sampling techniques, and we can use like cross entropy loss. And we can then train using gradient descent through the entire model. So we just compute the loss here, we compute the gradients, and for either of those loss functions, we can now backpropagate through the entire model. And so the model effectively learns how to use the label information, for example, we have at the targets here to update all the model weights in this neural network graph here, and then learn an improved update function on the graph. And now I want to quickly go back to the very beginning where we said, okay, the goal of graph representation learning is to learn embeddings for a graph like this, for example. And we can do the same thing now with graph neural networks. And let's say we have this very simple graph here that's called the Zachary's Karate Club. It's like a toy example that is often used to illustrate what graph representation learning methods do. And we can take just a randomly initialized 3-layer GCN model. So that's basically exactly what you see here, like this update function iterated 3 times. And these weight matrices here are just randomly initialized, just random matrices. We don't train them yet. And then we apply this, and then we say, okay, we project the output to 2 dimensions, so we can plot it. And now what we see here is that even when we apply a randomly initialized, untrained graph convolutional net, a GCN model, to this simple graph here, you already see that the output already kind of distinguishes the nodes to some degree. Like the nodes in this lower left corner here, they have a different local neighborhood structure, and they get embedded in a different part of this space. And this is really interesting to see, because effectively what you see here is that even without training, the model has an inductive bias to make use of the neighborhood structure and to embed things in such a way that it takes the graph structure into account, because different neighbors get treated differently based on, or different neighborhoods get treated differently just based on the message passing updates. So there's already an inductive bias there, and that will be very useful once you want to start classifying nodes. And that's effectively, that was the first thing effectively I did in my PhD. I implemented this model and I played around with some very simple tasks. And there, what I looked at was basically, okay, can we just label some of those nodes in these graphs and apply these losses at the end of the model and just backpropagate through this model, which was pretty novel at that time. Like, people didn't really do that for these kinds of models. And what we found was basically, let's say we only have 1 labeled node for each cluster here. So we just have 4 labels in total. And the task is to predict the node label of the unlabeled node. So that's what we want to solve. We want to see, okay, if the model can also color the other nodes of these clusters here correctly. And we take a very simple loss. We basically take a cross entropy loss that we've seen also before. Now, this is not a binary cross entropy loss, it's a softmax cross entropy loss, because we have 4 different labels, not just 2. And we have the GCN output, which is this matrix Z here, and we have a label matrix Y. And the interesting thing is we only apply the loss on the labeled node indices, which in this case are only 4 nodes. And the other nodes we don't apply a loss for. So effectively, this is a semi-supervised setup, because all the nodes are seen during training, but we only give labels for 4 of them. And that's why we call it semi-supervised classification. And this is really at that time was a very new way of doing semi-supervised learning, because we just don't apply a loss for the unlabeled nodes. And it's a very, very simple way to implement this. And now if you look what happens, if we train this model, so we start again from the randomly initialized, I'm going to start the video in a moment. We start again from the randomly initialized nodes, which are now zoomed out a bit. And then we apply gradient descent. So we optimize over, let's say, 200 gradient descent iterations, what the representations here look like. And then this gives us a nice update of these representations of the graph over time. And what you see here then happening is that these updates push those nodes to the side of the embedding space and really pull them apart. So after a few iterations, the model really learns to make use of those just 4 labels in total, 1 label per cluster, and really update the weights in this graph neural network model in such a way that the embedding space is really nicely decomposed, and all the nodes of one particular cluster end up, for example, in one corner. And this is just a toy problem, of course, with only a handful of nodes and only 4 labels overall. But the interesting thing is that this kind of, from this toy problem going to big real world graphs, nothing really changes. So we can basically take the exact same setting, and that's what we did in this paper back then, and scale it to bigger graphs. We didn't go to really big graphs. The biggest one had like 1 million nodes, but these days, of course, there's billion node graphs on the internet. We did effectively classification on citation networks. We just wanted to classify the paper category based on the network, but also based on the bag of words description of the abstracts of these papers. And so we wanted to classify the paper category, and the model was almost as simple as it gets. It was a 2-layer graph convolutional network where you basically can write it on a single line what the entire model is doing. You have an adjacency matrix. I put a hat here because we normalize in a particular way. You have the input node features, which are the bag of words features of your documents in your input graph, and you have these weight matrices here, which you learn in every layer. So these are the only 2 parameters you learn, W0 and W1, which are big weight matrices. And in the end, you have a softmax classifier. And so what we found back then is that against like all the state-of-the-art techniques in this space, some of them didn't use input features, but many did. And there was also one deep learning baseline, Planetoid, that didn't use graph neural networks. We found that, first of all, it was very, very easy to beat these methods by a very significant margin, which at first, when I had this result, I was like, oh, there must be something wrong. There must be a bug in my code. And I spent a lot of time trying to find the issue, but it turns out there was no issue. This was really the result we got. And it was also significantly faster. Like this runs in just mere seconds on these smaller graphs, and maybe in a minute on this million node graph. So this was a really surprising result. And when we got this out, then the community was equally surprised, I think, and it got a lot of attention. And so this is kind of like one of the first signs of lives we had. And later we also looked at the other problems like link prediction, for example. And so for link prediction with graphs, I don't want to go into too much detail here, but on the high level, the recipe is also very simple. And this is what we do in graph autoencoders. So you take an incomplete graph, because in link prediction, you have a graph which is not complete. You want to predict new links. And so you apply a GNN encoder, for example, the GCN, on the incomplete graph that is given to you. And then you have a small decoder. And this decoder is really just a pairwise scoring function. And this is very similar to these graph representation learning techniques I mentioned in the beginning. You have a pairwise scoring function. And you have a lot of design choices here. You can take an inner product. You can minimize the squared distance. And this predicts the probability that 2 nodes are connected given the scoring function. And we trained this with a simple binary cross entropy loss. We also used negative sampling here, all these nice tricks from the graph representation learning literature. And it turned out this works really well. And we only wrote a 2-page paper up on this topic, but it was also equally well picked up by the community, and graph autoencoders are forming now a very standard way of doing link prediction in graphs these days. Now, the last application I want to mention in this context here, before we dive into the broader application section, is how can we apply graph neural networks to, say, molecular data or like global graph problems? For example, predicting the biological activity of molecules. And Flex library together with Amea, who implemented the example. And there, basically, what we do is we have a simple graph neural network, like a graph convolutional network, that is applied on this molecular graph here. And now the nodes, the atoms we describe as simple like feature vectors, and the edges here are multi-relational. So we maybe have one edge type for a dual bond and a single bond and so forth. And the target is really just a multi-label classification. So we want to say if the target is active or inactive for various targets. And so really what you can do to solve this problem is you just apply, you take these input graphs and you take a big data set of graphs and you train graph neural networks to just predict the single output function, like I mentioned earlier. And this works remarkably well. And you can get very, very far with this simpler recipe. Now, if you want to do this, though, there's one big question, because so far when we looked at graphs, you just have one big graph and you do backpropagation on the entire thing. But with molecules, you have many small graphs. And if you have many, many small graphs, the question is, how do you batch those to make use of like GPUs, for example? And one strategy we came up with, which is also what is now used in practice today, is we just take the adjacency matrix of these individual graphs. For example, we have one molecule Q, one molecule V, one molecule W, and each of them have a small adjacency matrix, and we just put them together in one big adjacency matrix, but keep it sparse, so we don't compute message passing updates for all the empty rows here. Then we pass all of it through a single graph neural network that just doesn't communicate between these graphs because it's a block diagonal matrix. And then we reduce each of those graphs individually and predict a label from that. And so these are just some details. And if you look into typical graph representation libraries, this is how these models are implemented in practice. And this is just some detail for you if you wondered how you can actually use like these kinds of models on many, many graphs in practice. And so there's also the question of like, if graphs are vastly different size, how do you batch them? But there's a lot of research on that, on how to do that effectively. Now, graph neural networks didn't really stop there. And by now, they have really enabled a very wide range of impactful applications in a wide range of domains. And so I'm just listing a few here and a few references. If you are able to look at the slides later on, you can look some of them up. But basically, one example is traffic modeling. So you can take a road network, like, for example, Google Maps. So this particular paper that I'm citing here is graph neural networks applied to Google Maps traffic prediction or ETA prediction. And here, what you do is you take your road network, which is also a big graph, and you have little road segments that are your nodes or edges between them. And you apply a graph neural network to predict a particular output. For example, how much traffic is there going to be at a particular time point, given all the other information you have. You can also use graph neural networks to learn physical simulations. And I'm going to very briefly still go in one example here in a second part of my talk. And it's really like there's a lot of progress there in learning physical simulations. There's even a recent paper from DeepMind called GraphCast, where they use graph neural networks to learn weather simulations across the globe. And so one example is also protein modeling. So I'm mentioning AlphaFold 2 here. Of course, AlphaFold 2 isn't really the main novelty isn't really using something like a graph neural net, but of course this is a much bigger project. But you can like fuse some of those novelties in that model also under a graph neural network perspective. And in fact, a lot of people are using graph neural networks for modeling proteins or predicting properties on proteins. Then also things like large-scale recommender systems. In practice, a lot of companies at least have blog posts that describe how they use those. For example, Pinterest has a blog post on that, or Airbnb on how they use graph neural networks for recommendation systems. And things also like chemistry, drug design, material science, developing new materials. You can use graph neural networks in many of these examples. I see there's one more questions. The question is, many of the physical systems would be dynamic. So how is the time factor represented by graph neural networks? That's a really great question. And that basically comes to, there's basically two solutions to that. You can either view the graph as static and the features as dynamic. You just predict a new feature at a future time step from a feature at an old time step. That's how you can model dynamic information on a graph, which is what I'm going to show in a few slides. But it can also have dynamic graphs. So the graphs can also change over time. And so this is something like dynamic graph learning or temporal graph learning is something that is a very active research area. And there's many design choices one can make. You can, for example, say, okay, every 2 layers of your graph neural network correspond to 1 time step. And then the next time you apply a layer, the underlying graph might have changed in the system already. And so you also change the underlying graph. And so you can, the graph doesn't have to be the same for every message passing step. So you can change that over time, especially if your data changes underneath you. And so you can take into account these kinds of aspects. But there are many design decisions, and it's too much to go into here today. But it's a really great question. Now, I want to briefly still go into the second part of my talk. And because we already had many great questions, I'm going to cut this a bit shorter than I anticipated, but I still want to keep the floor open for maybe some questions. We still have the first part now, because the second part is really just a little cherry on top of the cake that we can dive a little bit into if there's enough time. But let's make sure everyone got all the details, or like got the main messages from the first part. So if any questions, let me know. I'm gonna, in the meantime, go to my slides and remove a few for the second part. All right. If there are no questions right now, let's keep questions to the end. Or also, if you have questions like earlier in between, then feel free to ask them anytime. I see there are 2 questions just coming in right now. Okay, so there's one question. Being deep networks, these are also prone to overfitting. How can we handle that for graph neural networks? That is a fantastic question. In fact, there are many aspects to this question. So, and they depend really on the problem. So there is both overfitting and underfitting issues happening in graph neural networks. Like if you apply graph neural networks on really large graphs, you can often have the problem of over smoothing, where because you have, say, some nodes that have a lot of neighbors, you average all the information from those neighbors in a single node, and then that information kind of becomes diluted, and the model cannot really extract that effectively anymore. Whereas on other nodes that only have like a single neighbor, it might be very easy to extract it. So the model kind of starts to overfit on these kind of simple to extract information from nodes, and starts to underfit on those kind of nodes that have a lot of information, because a lot of information gets lost in this averaging. And there's various ways of mitigating this. A typical way of mitigating this is using, for example, attention to pick out important neighbors, but also using skip connection, layer normalizations, things like the people use in transformers, if you're familiar with them. Those tricks can also be applied to mitigate these issues. Then there is the problem of overfitting by itself. Like, let's say you want to train on you want to train the best possible predictor, for example, for molecule classification. And it turns out that a really good way of dealing with overfitting in those aspects, if you really want to benefit from large models, is to use data augmentation. And so data augmentation is something that has been explored a lot in recent years, and you can add a little bit of noise to every node in your model, or noise to particular aspects, so you can augment the graph in some kind of way, and that helps with overfitting. So there's also a question about physics-informed graph neural networks. So I'll defer that to maybe later, because we're going to talk a little bit about physical systems in the next part of the talk. Then there's one question about how to handle uncertainty in graph neural networks. So uncertainty is interesting because it can come in various ways. Like you can, for example, have uncertainty about your prediction in the output. And then the same techniques apply as like for any other uncertainty modeling technique in any other neural network, which basically you can take an ensemble of methods and just look at like their discrepancy between predictions and say if multiple models predict differently, then there's probably a lot of uncertainty. You can use Bayesian approaches, like there's also Bayesian graph neural networks that take uncertainty into account. But then there's also maybe uncertainty or unknown features in your graph by itself, like you might not know about certain nodes if they're connected or not, and then actually attention or latent graph inference, what I'm going to talk about in a moment, can help you to infer these hidden features. And I'll go over 2 more questions, and then I'll continue with the second part. So in adjacency matrix, the rows and the columns are the same. Can it work if it's not similar? And there's also another question that is related to that. An adjacency matrix is always a square symmetric matrix. And so let me maybe answer those in one single response. So basically, an adjacency matrix, first of all, if you in a bigger picture, if you care about the description of how every node is connected to every other node, it's always square. But you can have bipartite graphs where you can only say, okay, you have one set of nodes, and you care about is how it is connected to the other set of nodes, and then it's not a square matrix anymore. So for bipartite graphs, adjacency matrix are not necessarily square. But for regular graphs, you would always have a square adjacency matrix. But then the rows and columns don't have to be the same, so they don't have to be symmetric. Like symmetric adjacency matrix you only have for undirected graphs, and once you have like directionality, you say, okay, this node really has a meaning that it's connected to this node and not the other way around, then the rows and columns are in that sense not the same. It's not a symmetric matrix. And the last question is, does it make sense to perhaps select a subsample of nodes for computing a loss during every training iteration for large graphs, or is that not necessary? That is also a very, very good question. So if you have very large graphs, this is in fact what you should do. Because if you don't do that, you would have to fit the entire graph, at least the number of nodes in memory and all their features. And that can become impossible if you have a very large graph. So actually, this is a really good point. So you don't only have to subsample neighborhoods, but you might even have to subsample the nodes in the first place that you want to consider if you have really large graphs. But typically, for node up to 1 million nodes or so, you can typically fit these things in memory. But these are all really great points. All right, let me continue to the second part of my talk. And this is about learning multi-object dynamics. So I'm showing just a very simple example here with 5 particles that are floating around. 1 second, let me try to stop those videos. So you have this kind of mystery 2D box where some particles are floating around, and the goal is really to model the system and to understand the system. But this is only really a small example. Of course, you can imagine when you can solve this, just like what we've seen earlier, once you can solve these toy problems, you can very likely scale this up to really big physical simulations of millions of particles, which is what the community has been doing in recent years. And so with this mystery physical system here, on the right-hand side, I'm just going to show what's underlying here. So this physical system is generated by multiple particles connected by some hidden springs, and this one violet particle just bouncing around by itself. And the goal here is really to have a model look at the observational data on the left here without knowing these hidden relations, and to really understand the physical system just purely based on what it sees. And ideally, for interpretability, maybe even giving us the interpretation on the right and telling us, hey, there are springs that are connecting these nodes. So that's kind of really understanding physical systems from observational data, which is a very important topic. And the way we can approach this is to we want to learn a dynamical system of these like particles, which we can now describe, for example, using a vector, which describes, for example, the position and the velocity of the particle. We enumerate those particles here from 1 to 5, and we assign a time step to each of those observations across time, because now we have a temporal system. But we want to model the interactions and their effect on dynamics, because these particles don't just swirl around in isolation, but it's really like an interacting system. And so that's where graph representation learning comes in, because if you want to model pairwise interactions, it's effectively a graph, even if the graph is fully connected, even if everything interacts maybe with everything. And now, before graph neural networks, a very typical approach to model these systems would have been the following. So we take these 5 particles and their trajectories, and we concatenate those feature vectors into a single global feature vector. And then we feed those into a single neural network. And so we would, for example, just choose a certain ordering from 1 to 5. We concatenate those and feed them into a neural network to predict the next time step, or use an RNN or an LSTM for that. And that works surprisingly okay. But there are many problems with this kind of approach. First of all, we did an arbitrary ordering of those nodes to achieve that. Whereas the physical system is kind of invariant under permutation on the physical laws. Like if you permute this ordering, the output will still be exactly the same. And the model also doesn't know about the structure of these interactions. So if there are pairwise interactions, this concatenation, what we've just seen, doesn't really take that into account. And in most physical systems, interactions are pairwise as a very good approximation, at least. And so graph neural networks are actually a perfect candidate because they actually do have this permutation invariance property. To be more precise, a permutation equivariant. If you're familiar with that, I'm not going to go into too much detail. And they model pairwise interactions. So graph neural networks are an ideal candidate for modeling these physical systems. And it's not a big surprise that they are really used a lot in practice for all kinds of physical problems these days. And so when we want to use a graph neural network for an interacting physical system, we can learn to model like the physical dynamics of an interacting system with high precision. This is something that a paper from Peter Battaglia, DeepMind, and others back in 2016 already showed with a very simple form of a graph neural network. They didn't call it a graph neural network at that time because it was just a single layer of a graph neural network, but it was kind of a good predecessor of graph neural networks in that space. And in this paper, Interaction Networks for Learning About Objects, Relations, and Physics, they basically showed that a model like this can learn to imitate the physical dynamics of a system just from observations. Not from video here, but they have the ground truth positions of every node, but they can really model the physical dynamics very accurately. And now, another question that I already mentioned at the very beginning is, what if you would also, on top of that, like to learn an interpretable model that also tells us about the underlying structure of these interactions? Because now we have a graph model, we can maybe use that graph model to give us that information out, like how these things are interacting. For example, which nodes are connected and which nodes are not connected. And now, this is something that we looked into this we looked into this problem in this paper called Neural Relational Inference, which is from 2018, but it's still a very timely kind of model, because effectively what it does, it learns to simulate a dynamical system while also inferring the underlying interaction graph. And now I can go into more details here of the model. I see. I was just wondering how much time we have left in terms of the talk. I think the talk can go until 12:30, including questions. Is that correct?
And the talk is up to 5 p.m. here, according to the Indian Standard Time.
Oh, right.
So it is
right. Sorry.
Yeah, it's 12:30 from 10.
Yes.
Okay, perfect. Yeah. So I was thinking about my time zone right now. Exactly. So like we still have half an hour roughly left, so I can go in a bit more details, and then we can take some more questions. All right. So the method here, neural relational inference, effectively processes in 2 steps. So first of all, we already learned about graph neural networks, and we're going to see again a little bit how a graph neural network can be employed here to learn to simulate a dynamical physical system. But then we also want to infer this hidden relation graph to really tell us about missing information or tell us about uncertainty, like the question we had before. And we do that using a variational autoencoder. You have a separate lecture on variational autoencoders later in a winter school, so I'm only gonna touch upon the very basics here. But effectively, if you combine these 2 models or these 2 ways of doing inference, you can effectively learn a model that learns to simulate dynamical systems while also telling us something about the underlying structure of the system. And the way we do this is effectively by first observing those dynamics. And again, as I mentioned before, those dynamics are described by feature vectors like position and velocity of every node at every time step. And we have time steps 1 to t here. And I've already absorbed all of these different nodes we have in a single representation here. So I'm not mentioning the node index here anymore. And then we run a graph neural network on this representation here. But the important thing is now, because we don't have a graph, what we do here is we take a fully connected graph. We just say everything is potentially connected to everything. And as long as we can afford it, we can always just run a graph neural network on this fully connected graph. And so this graph neural network now, instead of directly predicting a node label or a link like before, what it does, it proposes a latent variable. It proposes like what it thinks the interaction graph would look like. So proposes an embedding for each possible edge in the graph, which basically describes the probability that 2 nodes are connected. So it's a little bit like a link prediction system, but now without directly putting a link prediction loss. We don't have ground truth labels for it this time. But what we can do, because we don't have ground truth labels for these edges for which we do link prediction, we can apply another graph neural network, and that now operates on this predicted graph. We just take, okay, now this is the graph that the first graph neural network predicted. We run a graph neural network on that predicted graph, and we try to reconstruct or predict the future dynamics of the system. So the output now is to predict the positions of every particle at, for example, future time step. And because it has to go through this bottleneck here, it has to make a decision about how the model is connected, how the graph looks like. In order to do well at this prediction task, the model learns to both predict the dynamics and to give you a reasonable graph. And this is a very general recipe. So I'm showing this here for physical simulation. But if you don't have a graph, you can use this kind of latent graph inference, or in this case, neural-relational inference, to infer these missing informations. And so now this is effectively what we call a variational autoencoder, where you have an encoder and a decoder. So the first part of the graph neural network is an encoder, the second part is a decoder. And then we have these latent variables, which are these proposed interaction graph types, edge types. And we train this by basically sampling from this predictive distribution. And by having a reconstruction loss that is now written like this, you don't have to worry about the details. This might be clearer if you have the VAE, variational autoencoder lecture later on, but you also have a regularization term. And this is now different from pure supervised learning, because you need some kind of additional regularization to tell you whether a solution is more likely or less likely. And so this tries to put the predicted or inferred graphs here close to some prior distribution. You need to put in some prior knowledge. You need to say, okay, I have confidence that like 50% of the graph is most likely connected and 50% of the graph is unconnected. And this is something you can put in this prior distribution here. And then you have a regularizer that helps you stick to that prior. And so this is how you can train these models. And effectively what you do is you just backpropagate through the whole thing. And you have a little sampling step in here, which basically just involves adding some noise, and you have a regularizer. And this just gives you an example of how you can piece together parts of graph neural networks with other techniques to get something really powerful out, like a model that can learn the physical dynamics, but also give you interpretable like graph results as an output. And so we tested this on a range of toy environments at that time, where we have, for example, a little 2D box where we have some balls that are swirling around that are connected by invisible springs. And spring just here means it's the force that drives the interactions is just a spring constant times the distance of the particles. We also had a charged particle simulation, which looks a bit more interesting, where the forces are Coulomb forces, where you have this Coulomb constant here, and then you have like the charge of the particle basically. And the force is attractive if they're opposite charges, and it's repulsive if they're the same charge, like they can be positive or negatively charged. And it's it degrades by the squared distance, that force. That's why we have this term here. And we also looked into more complicated dynamics of like a nonlinear interaction model that is called the Kuromoto model, where you have multiple different particles that oscillate, and they're coupled by a sinusoidal force based on their phase difference. So I don't have to go into details here, but basically just we try to find a system that has some really complicated nonlinear force and try to see if we can also model that. And so it turns out, first of all, we can all model these kind of environments very well. Like the model can basically learn to imitate a physics simulator. But what you can see here in these high numbers and these bold numbers is the accuracy of how well we recover these latent interaction graphs that are usually given to us, so that are not given to us by the environment, that are used to generate the data. So there's some hidden interaction graph there, and the model without supervision has to recover them. And especially for the spring and the Kuromoto simulation, you can do it almost perfectly without any supervision. For the charged particle simulation, it's like 82%, which is not perfect, but it's pretty good. And the problem here is it's sometimes difficult to infer the interaction because some particles, if they're far away, they don't interact with each other very much. And sometimes they just don't cross paths. For example, the orange and the green particle here are so far away, they never get close to each other. So we don't really know if they're attractive or repulsive in their interaction. And that's why the model has a lot of uncertainty here. But the TLDR here, or the takeaway, is that NRI, or neuro-relational inference, can really discover ground truth relations of a very high accuracy. And neuro-relational inference has since been applied to a range of other setups and domains. For example, it can also be used for causal discovery. So what we've shown just now is looking at interaction graphs, but it turns out if you look at the problem of causality, where you really want to figure out if one thing causes another thing, so it's more like a directed interaction, you can put additional constraints on this model to give you directed interactions and use it for causal discovery, which is really exciting. And another aspect is you don't always have to just discover some unstructured graphs or undirected graphs, but you can also, for example, put additional constraints on the graphs you discover. For example, you only want to allow for spanning trees to be discovered. And so there was this paper called Stochastic Softmax Tricks, and they were able to include additional constraints on the kind of graphs you want to model or discover. And for example, in this case, you have some kind of example here and you want to model the latent spanning tree. And this is just a toy example here, but you can do this on more complex settings. Now, before we wrap up, I just briefly want to talk about some popular graph neural network libraries, because effectively, if we want to use graph neural networks in practice, the best starting point is probably to go to one of those libraries. They have plenty of examples. You can see all the code and details, the link to all the papers. You can learn a lot about those models in a hands-on kind of way. And I wouldn't just recommend using those models and just applying them, but also trying to re-implement one of those, for example, in one of those libraries. Like take one of the models without looking at the ground truth solution, just look at the paper and try to re-implement the model and see if that works. That's usually one of the best ways to learn about them. But one of the most popular graph neural network libraries is probably PyTorch Geometric. It's based on PyTorch and is used very widely. There's also the DeepGraph library that supports both PyTorch and TensorFlow. That also has a wide variety of application settings and benchmarks and neural network models implemented. There's Giraffe from DeepMind, where I was also involved in the development. It's based on JAX, which is a neural network or like automatic differentiation library frequently used at Google. And it allows you to more effectively apply these methods for, say, scientific data and scientific simulations, because it's much easier to get like second order gradients. But also, if you want to, for example, use TPUs, like Google's cloud TPUs, then JAX is like the very best way to interface with those if you want to, for example, run these things in an online collab. Then Giraffe is a really good starting point, and I think also has some really clean implementations of like the core representatives of attentional, convolutional, and message passing neural networks. There's also Spectral, which is in Keras, which gives a very high-level API, and it's a very easy starting point if you just want to use something. It's not as strongly maintained. It only has a single maintainer, but it's a really great instructional starting point. But there are many, many more, and if you just Google a bit, then you'll find a lot more of those libraries. Now, if you want to do further reading, there's a range of books on this topic. One of the first really well-written books on graph neural networks and a wider topic of graph representation learning I would recommend is this book called Graph Representation Learning from Bill Hamilton. I've also written a PhD thesis on this topic that I tried to keep in a very kind of instructional form, and this you can find for free online, and basically describes everything I had in my talk today. And this is something you can use as something to look up more about graph neural networks as well. There's a recent book on geometric deep learning, which describes a wider set of problems that doesn't just include graph neural networks, but also how to include symmetries, like 3D spatial symmetries and other geometric aspects into deep learning architectures. It's a very kind of more theoretically motivated book. If you want to go into those details, they also have a really great introduction to graph neural networks. I can highly recommend it. It's still under development, but there's already an early version of the book for free online. And there's also great blog posts that you can use to learn about graph neural networks more. For example, Michael Bronstein, who's also the first author of this book, has an article series on Medium. You can just also find it by searching for it on the internet. This is one really nice article I want to highlight here by Rishabh Anand. He wrote a blog post on graph neural networks for novice math phonetics, which I think is really beautifully illustrated, gives a lot of great introductory material. So these are great starting points. There's, of course, a lot more material and also YouTube lectures on the internet if you want to dive deeper into this topic. And with that, I'd like to acknowledge all my co-authors. Of course, all of this work has been the work of many collaborators across my PhD mostly. For example, GCNs, graph autoencoders, and relational GCNs were with co-authors at the University of Amsterdam and VU Amsterdam, which is the other university in Amsterdam. And neuro-relational inference was in collaboration with the University of Toronto. And with that, I'd like to thank you for your attention. It's been now almost 2 hours. I think we have about 15 minutes left for questions. So please go ahead.
Thank you, Thomas, for the extremely detailed and very well illustrated talk. Already we have received a number of questions, but session managers, please open the floor for further questions. And also unmute the participants if they want to ask vocally.
Yes, all the participants are unmuted. You can ask speaker the questions directly.
I'm having one question. Okay, so I'm thinking this graph. Am I audible?
Yes,
I can hear you.
Okay. See, there are. I feel these graphs can be visualized as a social network graph. This is also one type of graph. Okay, where I can do a mining based on different type of relationship and based on type of various property. I can do clustering on top of graph. Okay, and I can do various type of search also. That is also is possible with the help of GNN. Okay, but again, another type of graph is also that in a industry there are so many assets. They are not of similar type. They are of different node and different properties. Okay, but there is some relationship flowing across to come up with a process outcome or the plant outcome. Okay, so that is also graph. So how you segregate these two type of graph and address a problem statement?
That's a really great question. So I think what you referred to in the second part. So first we looked at mostly like homogeneous graphs that have the same kind of type of node features or type of nodes. But what you refer to is often called a heterogeneous graph, a graph that has like multiple different node types, like a node that describes an image or a node that describes a text document, and all living in the same graph. And the interesting aspect is we can actually treat all of that with the same framework, because effectively you can just embed an image and you can embed text in the same space using a pre-trained embedder, for example, and then just treat it as a homogeneous graph. That's one way. You can also define special, like just you do with a multi-relational graph in this setup here, where we have multiple relation types. You can also assign multiple weight matrices for different node types. So that's another thing. Like if you have really different types of nodes, that like a node that describes an image, a node that describes a user in a social network, you can use different embedding functions here. And they don't even just have to be linear matrices. You can even use a small neural network itself to embed that, or even a convolutional neural network for an image to get that image embedding. In practice, you would want to pre-compute those. You don't want to run both a convolutional neural net for images and the whole message passing in a single model. That would be too expensive, typically. You would probably use a pre-trained model to embed all the images, a pre-trained model to embed all the texts, and then just use those features in your model, and then just put them all in the same space. And if they're really in different space and you cannot embed them in the same space, then one good solution is also to just make a bigger vector, and then have like these or basically have a bigger vector where only the first part is reserved for the image embedding and the second part is reserved for text embedding, and just keep them separate. Or you have different linear embedding matrices like here, but then for different node types. So there's a lot of design decisions, and people have looked into various options, but there are solutions. Yeah.
Okay, so as we have told that it is expensive, say my every day I am having this heterogeneous graphs and these properties just keep on changing, and the system is also not that mature that it is having significant of data for the past huge time I can capture. Okay, so so if it is expensive for training of such type of model, how much time it may be if there are say around thousands of different nodes, around 1 lakh different nodes?
That's a great question. So I think if you have like 1,000 nodes or so, and if you can pre-compute their features, like if these nodes describe images, for example, then the most expensive aspect is actually getting those pre-computed features. And running the graph neural network then is really cheap. Like if you have 1,000 nodes, you can train a graph neural network model in a matter of like a minute. So the difficulty is really getting everything into the same embedding space, but I wouldn't do that in a single big model usually, although there are people trying that.
Okay, okay. Thank you for your answer.
Yeah, thanks for the question.
Hello, actually, I have one question. Am I audible?
I can hear you. Yeah.
Okay, so I have one question that suppose I'm applying GNN on 50 nodes and I'm applying same model GNN on 500 nodes. So can you comment on the performance, like it requires large number of nodes or it will work well for small number of nodes also?
That's a great question. And so I think one thing we've seen in this toy example only has, wait, a few slides further. This toy example only has really like a small number of nodes. I don't remember the exact number, but it's, I guess, on the order of 30 nodes or so. And as you can see here, it works pretty much perfectly. So it of course, it depends on your data, but you can tune a model in such a way that it does really well on small graphs as well. You have to be careful with the number of parameters you put in your model. Like here, you want to use fewer parameters. You want to use smaller weight matrices. Whereas if you have bigger graphs, you can afford bigger weight matrices and maybe deeper models. So these aspects matter, but there are ways of making these models powerful even on small graphs.
Okay, thank you.
Thanks for the question.
Hi, sir. Am I audible?
I can hear you, yes.
Okay. Can GCN be used for in distributed machine learning technique?
So the question, if I understood correctly, is whether GCNs, for example, can be used also in a distributed machine learning setup. by distributed, I guess you mean over multiple devices. It's like multiple GPUs, maybe even multiple servers that communicate with each other. Is that correct?
Yes, yes, sir. Like IoT system, basically IoT or cloud computing. There are many sensoring nodes, or many things in a collaborative manner, or zero touch provisioning system like that. So can we use here, or it is useful or not, like that?
That's a really great question, and I think it depends on the details. So in fact, a lot of the big graph neural networks people train, for example, for simulation, but also for other big graphs, are using distributed setups. They use multiple GPUs that are interconnected, but typically still on the same machine. You can also use multiple servers that are interconnected and train models, but then you basically run into a lot of technical challenges. These can be overcome, and some people are working on this, but it's not straightforward. So the short answer, so the long answer is basically, the short answer is basically yes, distributed setups make a lot of sense for these kinds of models, especially if you want to scale. But if you want to be like, very often it's advisable to try to fit it on a single machine and maybe try to really do the inference and the training on like maybe a single machine, maybe with multiple GPUs or TPUs to start with.
Thank you, sir.
Yes, thanks for the question.
Sure. Hello, sir. Am I audible?
I can hear you. Yeah.
Yes, I have one question. I have seen that most of the papers of graphs mostly relies on the message passing and like neighborhood aggregation techniques. Is there any future scope like the beyond message passing? Is there anything there?
That's a great question. So I think overall, a lot of like there's a lot of work in like this idea beyond message passing of using other techniques. Effectively, what they all amount to, or what most of them I would say amount to, is just rewiring the graph and then applying message passing again. So you can almost all methods that go beyond message passing, interpret them as just applying message passing but on a different graph. And so effectively, I think you can basically go very far. I don't think there's a exhaustive proof that every method can be phrased as message passing on a graph, but effectively, I think the message passing framework, if you keep that in your mind, you can describe a lot of different methods with it.
Thank you.
I see there's one hand up by Anirudh.
Any more questions?
Yeah. Yes. Hi. Thank you.
Hello, sir.
Yes,
can you hear me?
Let's go with Anirudh first. He had his hand up.
Hello.
Yeah. Okay. Thank you. Thanks, Thomas. Thank you for a very interesting talk. One quick question on this physics-informed graph neural networks. So I understand the basic physics-informed neural networks, but what are the other ways in which you have seen physics being embedded in the graph neural network?
That's a great question. So I think there's a number of like interfacing with physics and graph neural networks. One is to just use a black box graph neural network to model physics, which is kind of what I've shown you in the very end. Right. But that's not what usually people would call physics-informed graph neural networks. There's also physics-informed graph neural networks in the sense that you use physical properties in the graph neural network. Like for example, you hard code certain aspects of the graph neural network to be physical force functions, and you just learn the parameters. In fact, in this setup here, you can actually basically the graph neural network you apply here, the message functions. Let me actually go a few slides back. I think there's one slide which illustrates it nicely. In this setup here, these edges and these edge update functions, I mentioned the connection to physical forces earlier. And so if you know the force, or if you know the functional form of the force, you know it's like an inverse square law force, for example, then you can hard code this here. And you can just learn the parameters, like you can learn the force constant or a multiplier. And the rest you can keep all learnable. And this is one way of doing physics-informed machine learning with graph neural networks. If you know physical quantities, you can put them in here as a ground truth. There's another one some people call physics-informed learning if they have another loss on like making sure that this function here is close to the actual force. You have an actual force loss. So there's a number of ways of doing it. Like you can hard code, you can have a loss to make it more similar to forces, or you can just imitate Kipf's model of physics. So these are typically the ways people do it.
Oh,
great.
Okay. Thank you so much.
Thanks.
Hello, sir. Can you hear me?
I can hear you. Yes.
Sir, I have a question, sir. For this, you said that for normal graphs or like, then you don't regular graphs. You don't need that undirected. Means the adjacency matrix will be nice. Will be square matrix, and then it will. If you take undirected graphs, that will be symmetric. But in the case of multipartite or in the case of bipartite or multipartite graphs, then what we can choose means how can we choose the adjacency matrix in that case? So
that's a great question. So for bipartite graphs, you can always still have a full square adjacency matrix. Like basically, you can ignore the fact that it's a bipartite graph and just treat it as a normal graph, because a bipartite graph is effectively a normal graph. It's just certain edges follow a certain pattern. So that you can always do. You can be a bit kind of more informed about it, and then actually choose like a special bipartite message passing scheme. So we had one paper around this called graph convolutional matrix completion, where we basically use graph neural networks like here for recommender systems, where you have a bipartite graph between users and items. And effectively, you then only pass messages from users to items and items to users, which boils down to having two adjacency matrices, one that goes from users to items and one that goes from items to users, and they're both rectangular. So if you're interested to learn more about that, I recommend looking into this paper called graph convolutional matrix completion.
Sir, can you just write this in the chat, the name of the paper?
Yes, let me write this. That's a great idea. Let me write this in the chat. Graph convolutional matrix completion. Yes. I see there's one more question that I haven't answered in the chat. Let me take this as the last question and we're at time. The question is, will this be applicable for univariate time series forecasting purpose instead of spatial temporal? That's a great question. So for univariate time series forecasting, so basically you have a single variable that you want to forecast in time instead of just spatial temporal. I would say this is possible, but you would really want to have like some interesting interaction information. So I mean, in some sense, what we've shown here in this example of these Kuramoto oscillators on the upper right side, this is a single variable that you predict forward in time, and you have 5 of these that are interacting. And so this is not really spatial temporal, but this is really univariate in some sense. So yeah, the short answer is maybe yes, but maybe that's not what he had in mind.
Thank you, Thomas, for this wonderful and insightful talk. It's already 5 p.m. I think it's 12:30 on your side. And
yes, exactly.
Let's conclude the session here. And this is a very insightful and elaborative talk. Thank you.
Yes, thank you so much for the invitation again, and thank you for all the great questions. It was really very insightful for me as well to see what kind of questions come up. Yes, and thanks everyone.
Hope to see you in the next winter schools, next WSDL.
Yeah, just let me know. Thanks.
Yes. Thank you. Excellent.
Right. Thank you. Bye, everyone.
Bye.